Hello, everybody. Last time we talked about the Diels-Alder reaction, and today I want to talk about some more reactions that fit into the category of pericyclic reactions. And so I want to talk about the Claisen and the Claisen and the Cope rearrangements. Okay, first up, Claisen rearrangement. All right, so every reaction has a recipe. You're always looking for the starting material. And for the Claisen rearrangement, what you're looking for is either a vinyl allyl ether or a phenylallyl ether. So in this reaction, you're looking for a vinyl I don't like the way I do that. Try again. So this is called a vinyl allyl ether. So vinyl allyl ether. Okay, so it's an ether, and this two-carbon component over here with the double bond, that's vinyl. And this three-carbon component up here, 1, 2, 3, that's the allyl. So you're looking for an ether where the oxygen atom is tucked in, is bonded to a carbon-carbon double bond on one side, and it's bonded to a spacer carbon and then a double bond over here. So that's what you're looking for, vinyl allyl. And the other possibility is where the vinyl double bond is part of a benzene ring. So the other possibility would be, so there's that three-carbon component, 1, 2, 3, with that double bond at the remote end. And here's the vinyl double bond, but sometimes this vinyl double bond can be part of a benzene ring. So that's the recipe. That's the recipe for the Claisen. This guy would be called phenyl. That's the benzene ring. Phenylallyl ether. Okay, so those are the starting materials. The reaction conditions, heat, and it's a pericyclic reaction, so a bunch of bonds are moving all at the same time. So this bond moves up here, this bond moves over here, and this bond moves down there. So the vinyl allyl ether must be in the C-shaped conformation. If you saw the discussion about the Diels-Alder reaction, we also saw there was a C-looking thing involved there as well. So this vinyl allyl has to be able to adopt the C-looking conformation. And see this gap over here? I'm going to put a little star at the end of the allyl double bond. I'm going to put a star at the end of the vinyl double bond. And you see how these two carbons, there's a gap here. Okay, so all of these electrons move around, and we get those two stars end up hooked up to each other. There used to be a gap. Now that gap has been closed. And this bond to the allyl end of the ether, that's gone now. So we go from an ether to an aldehyde or a ketone. It's going to be an aldehyde if there's a hydrogen there. It's going to be a ketone if there's an organic group there. Okay, I'm also going to put, all right, so now down here, this is a little bit slightly more complicated. So once again, I'm going to put a star at the end of the allyl double bond, the remote end of the allyl double bond. I'm going to put a star at the far end, the remote end of what you could think of as a vinyl double bond, but this isn't really vinyl. It's now a carbon-carbon double bond in benzene. And once again, all of these bonds, all of these electrons move all at the same time, and these stars get hooked up. See how there's a gap here? They get hooked up, and notice that across the way from the gap, this bond is gone. Notice that across the way from this initial gap, this bond is now gone here. So the stars hook up. And there's what is left of my benzene ring. This is heat. All right, the phenylallyl system is a little bit more complicated than the vinyl allyl system, because now what this molecule will typically do is undergo a tautomerization, which will allow the benzene ring to re-aromatize. You know that benzene is thermodynamically pretty stable. This thing wants to tautomerize in order to bring back the benzene ring. Okay, so if you remember about tautomerization, you're looking for a double bond, a single bond, and a bond to hydrogen. So over here, I'm just going to review the keto-enol tautomerization. Double, single bond to hydrogen. Oh, it makes too big. So this tautomerizes, T-A-U-T. The double bond and the single bond in this unit change places. And the hydrogen at the remote end of the tautomerizable unit appears to jump from the single bond end to the double bond end. Okay, so this is supposed to say tautomerize, so that's just a review of the keto-enol tautomerization. One of the things that we talked about is that the keto form is usually more stable than the enol form, but not here, right? This is the keto form. But when this thing tautomerizes, it's going to bring back that benzene ring, which is much more stable than what we have here. So I'm going to put this guy in brackets. He's not going to be around for very long because he's going to undergo the tautomerization. T-A-U-T, double, single, bond to hydrogen. So the double bond and the single bond change places. The double bond and the single bond change places, and this hydrogen appears to jump from the single bond end of the tautomerizable unit to the double bond end of the tautomerizable unit. So you actually get this phenol, right? This benzene ring that has an OH group on it. Okay, so that's the Claisen rearrangement. You're looking for a vinyl allyl or phenylallyl ether. Put the double bonds in that system into this C-looking thing. You have a gap. That gap becomes a single bond, and across the way from where that gap used to be, that's gone with the motion of these double bonds. Okay, so let's try some product prediction. All right, so what about this thing? heat, draw the structure of the product. Well, is it a Claisen rearrangement? Oh yeah, because the recipe for the Claisen is there. You're looking for an ether oxygen. And on one side of the ether oxygen, you have the vinyl functionality. What's that? It's two carbons tied together with a double bond. On the other side of the ether oxygen, you're looking for the allyl moiety. What's that? It's going to be an sp3 hybridized carbon, which is also bonded to a double bond, right? So this is the allyl portion. This is the allyl. And this guy up here, maybe do it this way. That's the vinyl portion. Yeah. So the rest, it's the recipe for the Claisen. Problem is the way this has been written. This is going to be very hard to figure out what's going to happen. What you're looking for is to draw the vinyl group and the allyl group in that C-looking thing, right? And that's going to make keeping track of the motion of the electrons and where the new double bond pops up easier. So I'm going to take this and I'm just going to rewrite it, right? Maybe equilibrium arrows here showing that this is another conformation. And I'm going to get the vinyl group and the allyl group into that C-looking thing. So I'm going to put a little star at the remote end of the vinyl group. I'm going to put a little star at the remote, the far end of the allyl group. And believe it or not, these two stars, although they look a million miles away from each other right now, they're going to hook up. But that hookup is really only apparent when you draw this allyl vinyl allyl system as a C. So there's my vinyl group. It's part of a cyclohexene ring. There's my oxygen atom. There's my allyl group. Now I've written it in that C-looking conformation. And so this carbon, which I call the spacer carbon, that has two methyl groups on it. So all I've done is I've transformed this into an appropriate conformation, which is going to make drawing the product of the Claisen a little bit easier. Okay, so these electrons go up here, these electrons go down up there, and these electrons go down here. So there's the gap, right, between these two stars at the remote ends of the allyl and the vinyl group. They're going to hook up. Initially, across the way from the gap, there's a single bond to oxygen. That's going to be gone. There's my star, one of them anyway. It hooked up with my other star. Double bond there, two methyl groups there. The original single bond between the oxygen and this gap, that's gone. There's a new double bond here, hooked up. And so that would be the product of this Claisen rearrangement. Okay, so pretty tricky. How about let's try again? Heat. Draw the structure of the product. It's the recipe for the Claisen. I see an ether oxygen. On one end of the ether oxygen, I see a vinyl group. On the other side of the ether oxygen, I see an allyl group. So you want to draw the vinyl group and the allyl group in that C-looking conformation. And you want to hook up the remote ends to a new single bond. So I'll give you a second to try to come up with the product here. Okay, so here's my allyl functionality. Spacer, then carbon-carbon double bond. That's the allyl. On the other side is what I can consider, although it's not really a vinyl group, it's this carbon-carbon double bond directly bonded to the ether oxygen. The remote, the far end of the vinyl moiety, I'm going to put a little star on him. The remote end, the far end of the allyl moiety, I'm going to put a little star on them. And these two stars, even though they look a bazillion miles away from each other, they're going to get hooked up. But it's going to be easier if I try to redraw this with that C conformation. So I'm going to try that. Okay, there's my benzene ring. I want a C off to this oxygen, then my spacer. There's my spacer, and then here's the double bond of the allyl functionality. There's the remote end, the far end of the allyl functionality. I got it into that C-looking thing. Well, it's kind of like backwards. So all of these electrons move at the same time. There's the gap between my two stars. There's the gap between the remote ends of the vinyl and of the allyl. There's going to be a new carbon-carbon bond there. And the bond diametrically opposed, that's going to be gone. So I'm hooking up my two stars. New double bond here. New double bond there. Okay, but I can't stop here because I recognize that this is the keto form of a more stable enol form. Why is the enol more stable? Because tautomerization here will bring back the benzene ring. So I'm putting him in brackets. He's not going to be around for very long because he tautomerizes. Double, single, bond to hydrogen. The hydrogen jumps to the double bond end of the original, and the double bond and the single bond change places. So now I'm ready to draw the final product. Here's my benzene ring. Here's the enol. And this carbon, there was my star. There's my other star. And so that would be the product. Okay, so those are some entry-level product prediction problems dealing with the Claisen rearrangement. How about let's add an extra level of complication, and that is, let's talk about the stereochemistry of the Claisen rearrangement. All right, Claisen rearrangement, stereochem. And the guiding principle here is chair-like transition state. Okay, so rocketing up to a higher level of complexity, something like this. Heat. Okay, so is it the Claisen? It is. There's the vinyl functionality up here. There's the allyl functionality up here, down here. Allyl is spacer, then double bond. Okay, and I also have done the grace and favor of drawing this already in that C shape. But now what? And so here's the gap, right? Here's the gap. And I'm going to have a new double bond there. There's my star. There's my star. Those are the remote ends of the vinyl and of the allyl functionality. They're going to be hooked up. But when they hook up, that's going to create a chirality center there. And when they hook up, that's going to create a chirality center here as well. I want to know, and what I'm talking about now, is what is going to be the relative orientation of these methyl groups in the product. And the key is the reaction proceeds through a chair-like transition state. Okay, so this is pretty complicated, but I noticed that Professor Porco did mention this in the lecture, so I guess he expects you to know about it. Okay, so here's what I would do, is that I want to draw a chair that models this guy. So just lightly on my blackboard here, just what I drew is the outline of the chair. And now I'm going to try to fit this molecule into this chair. Okay, so so this oxygen, I could put the oxygen anywhere. It just makes more sense. Most sense if I put the oxygen there. And the back of this chair, I'm going to write this vinyl group here. So far, so good? Okay, notice this double bond here is trans, right? So I want to draw this trans. Like that, right? I'm drawing a chair, and remember a chair has an axial option and an equatorial option. So this methyl group here, there's my star, that's him. I drew him in the axial orientation, guided by the fact that this double bond here is trans. There's a hydrogen. Okay, now the rest of this, there's the bond to my spacer. There's my spacer. There's the double bond of there's the double bond of the allyl. There's the remote end of the allyl. These two stars are going to hook up. And see this double bond here? He's also trans. So I want to faithfully translate that into this chair-like transition state. So it's a chair. You have an axial option and you have an equatorial option. So to make this double bond trans, I'm going to put the methyl group in the equatorial position, and there's going to be a hydrogen there. Okay, and so now up here on this drawing that has no, that isn't a chair, remember what happens is the two stars hook up and all of these bonds, all of these electrons move at the same time. Same thing here, over there, this goes there, and this is going to go here. Okay, the product, I'm also going to draw that as a chair, but not as the chair flip because we don't have a chair flip going on here. So once again, just to guide my pen, I'm going to lightly draw the outline of the chair. Okay, so this oxygen was up here. This is now a new double bond. This is a single bond here. I had an equatorial methyl and an axial hydrogen. That was my star. Here's my other star. They're now hooked up with a single bond. This double bond used to be double bond, is now a single bond, and this single bond is now a double bond. Okay, and what's going on here at my other star? I had an equatorial methyl and an axial hydrogen. Okay, so that would be the product with its stereochemistry drawn. Now, if I wanted to translate this into a dashing and wedging, there's my oxygen, there's my star, there's my star, there's my new double bond. And notice in the original, the two stars were a gap, and there was a oxygen carbon single bond diametrically opposed. In the product, these two stars have hooked up, but once again, there's a gap now at the diametrically opposed position. I'm ready to translate this chair into dashing and wedging. This methyl group is down, that's a dash. This methyl group is up, that's a wedge. So the product has this stereochemistry. Pretty tricky. Okay, so ready to try one on your own? Heat. Draw the structure of the product. So I drew it in that C-looking thing. I see vinyl down below. I see allyl up above. This is the remote end of the vinyl. There's the remote end of the allyl. These guys are going to hook up. But it's going to hook up through a chair-like transition state. So this bond is going to be gone because that's the bond on the opposite side of this gap. And we're going to get a new double bond here. But with this methyl group on this wedge here, the question is, I'm going to get a new double bond here. Is that new double bond going to come out cis or trans? And so to answer that question, that's where we have to resort to the chair-like transition state. So what I do is I'm going to lightly draw the chair, and then I'm going to translate this guy into the chair. You can put the oxygen anywhere you want. To me, it makes most sense to put the oxygen there. And now there's the vinyl group. There's a single bond. There's the double bond. And here's the allyl group. Single bond, double bond. There's the remote end of the vinyl. There's the remote end of the allyl. they're going to hook up. What about this guy here? Well, this is the 1, 2, 3. This is the S absolute configuration. Yeah, that's the S absolute configuration. This carbon is this one. I have to make sure that I draw the S absolute configuration. And so that would mean, since this methyl group is on a wedge, that would mean that the methyl group there is equatorial, and there's a hydrogen there. He's axial. And let's see, is this S? What? Yep, this is the S absolute configuration. So it's important to translate the stereochemistry here to the chair. Okay, so now we move around all of these electrons. We have a chair once again, but it's not the chair flip. It's just the same chair that I started with. This oxygen is here. This is now a double bond down here. It was started life as a single bond. It's now a double bond. This double bond has been degraded to a single bond. That was my star. That used to be the remote end of the vinyl group. The two stars have hooked up with a single bond, like so. This double bond has been degraded to a single bond, and this single bond has been upgraded to a double bond. This hydrogen, this axial hydrogen pointing down, it's still pointing down. And this methyl group, I'm not going to draw it like that because that would be very unrealistic, because I know that this double bond is either going to be cis or trans. So this hydrogen here, he's my pal, he's my guide. He was pointing down here, he's pointing down here. This methyl group is now up here somewhere. So this double bond ends up being trans. Okay, so the product here, if I wanted to draw it using this figure, would be that, where that double bond worked out to be trans. Okay, tricky, tricky, tricky. How about, okay, so that's Claisen with some of the complications. A related reaction is the Cope rearrangement. Cope is just like Claisen in practically every way, except that this time you're nuking the oxygen atom. Oh, why am I so angry over it? Cope rearrangement. It's just like the Claisen, but you don't have an oxygen atom in the system anymore. So remember, Claisen looked like this. Claisen looked like that. Versus Cope, which has the very same architecture of the Claisen, except it's not an ether anymore. So what you have here is this 1, 2, 3, 4, 5, 6, this hexadiene. And just like with the Claisen, I'm going to put a little star on the remote end of the vinyl group. I'm going to put a little star on the remote end of the allyl group. I'm going to do the same thing over here. I'm going to put a little star at the remote end of one of these double bonds. I'm going to put a star on the remote end of this other double bond. And just like in the Claisen, we had this motion of electrons. We have the very same thing here in the Cope, like that. And so these two stars, they end up hooked up with a new single bond in between. Okay, so now they're stars. Now, how about some dots? Star, double bond, single bond. I'm going to put a dot here. Star, double bond, single bond. I'm going to put a dot there. And these two dots, they used to be bonded together, but they aren't anymore. So at one end of this one end of this hexadiene system, they get hooked up, and the diametrically opposed end used to be bonded together, but they no longer are. So the Claisen and the Cope, very related. Okay, so how about let's do some product prediction with the Cope. Heat, draw the structure of the product. Is it a Claisen? No, because the Claisen has a vinyl allyl ether. This isn't an ether, it's some kind of crazy alcohol. But I see that C-looking shape. I see that C-looking shape, and I see these two double bonds. There's my star. There's my star. There's the gap. Diametrically opposed to that gap, there will be my dots. The two stars start out not bonded to each other. The two dots start out being bonded to each other. But in the product, the bond between the dots is gone, and there's now a new bond between the stars, right? So I'm just using my stars and my dots to keep track of all of the bonds that are forming and being broken. There's one dot. He is no longer bonded to this dot. There's one star. He is now bonded to the other star. And there's a new double bond there and a new double bond there. Right, so it's just all of this. It's all very similar to what we saw in the Claisen rearrangement. So is this the final product? Oh no, because what do I see here? It's an enol. And we know that enols, it's an enol, and we know that most enols are unstable relative to their keto tautomers. In the Claisen rearrangement, we have a situation where the enol is more stable than the keto, because the enol in the Claisen can tautomerize, because the keto in the Claisen can tautomerize to a benzene ring. But I don't see the possibility of forming a benzene ring anywhere here. So this enol is less stable than the keto tautomer. So putting him in brackets, he's not going to be around for very long. He's going to tautomerize to the keto form. Double bond there, double bond there. So that would be the structure of the product. So that's actually a 10-membered ring. It's drawn in a hideously ugly way, but this is actually a 10-membered ring. Yes? Okay. How about some more product prediction with the Cope? Heat. Draw the structure of the product. Is it the recipe for the Cope? It is. I see two double bonds with two spacers in between. I see a double bond. I see two double bonds separated by two spacers. Only problem here is that I haven't drawn the structure with that C looking thing. So in order to, it's just easier if you can redraw the structure with that C looking thing. Right, this is the remote end of one of the double bonds, that's my star. That's the remote end of the other double bond, that's my other star. Here are my two spacers, they are my dots. Those two stars are going to hook up, the two dots are going to unhook, draw the structure of the problem. So I'll give you some time to try that. Okay, so here's a dot. Here's a dot. This dot off to that. This dot off to the double bond. There's my star. There's my star. This star is part of a cyclopropane. Right, so I just redrew my structure to get it into that conformation. So the dots are now at the ends of the new double bonds. The dots are now at the ends of a new double bond. The stars have hooked up with each other. Only this star is part of a cyclopropane. So there's the structure of the problem. Okay, let's see. Let's try one more. Oh, this one also has a triangle in it. Heat, draw the structure of the problem. It's a Cope. I see two double bonds separated by two spacer sp3 hybridized carbons. Here's my star. That's the remote end One of the double bonds. There's my other star. They're going to get hooked up. Here's my spacer. Here's my spacer. They're originally bonded to each other, but that bond is going to go away. So here are my stars hooked up. This double bond is now a single bond. This single bond is now a double bond. There's my dot. He used to be bonded to the other dot. That bond is gone now. Well, that looks very weird, but I think it's okay. And then this was part of a cyclopentane point. So that's a hideously ugly drawing, right? But it communicates the correct movement of bonds. This is a 1, 2, 3, 4, 5, 6, 7, and back again. So if I wanted to maybe write this in a prettier format, I might draw a 7-membered ring fused on one side to a 5-membered ring with a double bond there. That's my star. There's a spacer. I mean my dot. There's my other dot. There's a double bond there. There's my star. There's my star. Okay, so it's just drawn in a slightly different way. Okay, so to finish up, are you ready for a real brain buster? Okay, so remember what we're doing, right? Cope rearrangement. There's my star, there's my star, there's my dot, there's my dot. Heat. The dots become the remote end of a double bond. The stars get hooked up. The dots become the remote end of the double bond. Okay, so now what about what's going to happen here? Heat. Draw the structure of the product. Good luck. Although these, you might think that these stars and these dots, it really sounds rather infantile, does it not? But I found that that's like for some of these complicated rearrangements, that's just a good way of keeping track of which atoms end up bonded together, which atoms end up at the end of double bonds and all of this other stuff. So why don't you try this, see what you come up with. There's my star. There's my star. These two guys are going to be hooked up. There's a spacer. There's a spacer. The bond between these two spacers is going to go away. And this spacer dot here is going to end up at the end of a carbon-carbon double bond. The spacer dot here is going to end up at the end of a carbon-carbon double bond. And here's my so all the action is in here. Okay, so ready to draw the product. This dot is at the end of a new double bond. This star hooked up with this star, and this dot is at the end of a double bond. There's the product. Star, star, dot, dot. Yep, there's the product. So this, see, this is an allele. This is an allele spacer, carbon-carbon double bond. This allele looks like it took a walk to down here with rearrangement of that internal double bond. Pretty tricky. Well, that's all I have for you today. Any questions about anything? Any questions about anything before we sign off? Okay, well, I'll see you next time.